series representation for 1 over zeta. So here's the on the screen the series representation for 1 over zeta function, and this is actually sum from n equals to 1 to infinity of mu function of n by n to the power s, and then this mu function of n is the Mobius function, right? Its definition will be apparent like when we are at the end of solution, right? When we go to the solution, and then when we are about to end this problem, then it will be apparent how we'll be defining this function. And yeah, so basically this whole thing is just based on how we are defining mu of n, and we'll see. So before we go to the 1 over zeta of s, so first of all, let me also talk about zeta of s. This is actually the sum from n equals to 1 to infinity of 1 by n to the power s, right? So over here, the only difference is there's mu of n in numerator. Over here, like it's just 1. We also know that this is actually equals to like this product over p being a prime, right? And 1 minus 1 by 1 minus p to the power minus s. I guess you guys also know this like a definition for zeta, right? So basically, over all the primes, we multiply this 1 by 1 minus p to the power minus s. So yeah, like it turns out that we can actually use this product definition of zeta of s to make progress for 1 over zeta of s, right? So from here, we see that this 1 over zeta of s will actually be product in p being a prime of 1 minus p to the power minus s, right? Now after that, let me just write this properly, p being a prime of 1 minus 1 by p to the power s, right? So let's try to expand it. 1 minus 1 by 2 to the power s, 1 minus 1 by 3 to the power s, 1 minus 1 by 5 to the power s, 1 minus 1 by 7 to the power s, 1 minus 1 by 11 to the power s, and so on over all the primes, right? Okay, now let's try to see what happens, right? So over here, first of all, if we just take all the 1 we will get 1 we will get 1, right? So now if we take like negative 1 to the power 2s and all the other ones, we will have minus 1 by 2 to the power s. Now if we take, let's say, negative 1 by 3 to the power s and all other s just ones, we will have negative 1 by 3 to the power s. Do you think we can get like 1 by 4 to the power s? No, actually, because there's just this like 1 2 to the power s, right? So we cannot get that. So let me still write it as 0 by 3 4 to the power s, okay? Yeah. Now, if can I get 5 to the power s? Yeah, like you can just take minus 1 by 5 to the power s and all other just ones, right? So minus 1 by 5 to the power s. Can I get 6 to the power s? Yeah, you can actually take these two terms and then all the other just ones, right? So that will give you plus 1 by 6 to the power s. And again, minus 1 by 7 to the power s. Do you think we can get 8 to the power s? No, there's just 1, 2. So 0 by 8 to the power s, 0 by 9 to the power s, 0. Okay, what about 10 to the power s? Because 9 had 2 3s, so we cannot get that, right? But for 10, we can actually take minus 1 by 2 to the power s, minus 1 by 5 to the power s, and all other just ones, right? So that will give us plus 1 by 10 to the power s, right? And then we'll just get minus 1 by 11 to the power s, right? And for 12, we need 4 as well, right? Because that's 4 into 3. We cannot really get 4 because there's this 1, 2. So 0 by 12 to the power s. For 13, minus 1 13 to the power s. For 14, again, there's 2 and 7. So plus 1 by 14 to the power s. For 15, it's plus 1 by 15 to the power s. And then 0 by 16 to the power s. And then minus 1 by 17 to the power s. So what I'm trying to get is, I was actually trying to get up to, okay, so actually, okay, so what I'm trying to get to is, I'm trying to get to 30, because in 30 this is actually multiple of 2 3 and 5, right? So there are these 3 terms, so because of that it will be negative 1 by 30 to the power s, right? So over here, now based on these numerators, we will try to define this mu of n, right? So according to what we need. So first of all, it's the mu of n is just 1, like mu of n basically captures numerator, right? It's this one if n equals to 1, right? Now, if our numerator contains any squared prime number, so let's say over here, like in 8 we had 4, right? And we couldn't obtain 4 because there couldn't be two twos. Similarly in, like, let's say 12, we needed 4, right? But we cannot get 4 because there's just 1 2 over here. So if there's like any squared prime number, like, we cannot just obtain that, and the numerator has to be 0. So 0 if this n, like n basically means, I mean, this number, right? So like whatever the number is in denominator, so I mean, for that number I'm trying to find the numerator. Okay, so if n has a squared prime number, yeah, prime, I mean factor, yeah. Okay, so now if there's no squared prime factor, I mean no two same prime factors, and then in that case, like, if all of them are distinct, we can obtain that, right? But again, for that, let's say if we are using two distinct prime factors, let's say 2 and 3, then we will have positive sign. But if we are using, let's say, three distinct prime factors, we will have negative sign, right? So this sign is actually depending on how many prime factors are used, right? So okay, so okay, this will capture the phenomena. Basically, if k is even, then that's 1, but if k is odd, then that's negative 1, right? So negative 1 to the power k if n is a product of k distinct primes. Yeah. Okay, so now we know that. Now we can actually write this whole thing as just sum from n equals to 1 to infinity, and then mu of n by n to the power s, right? So like, it really looks simpler in this form, but yeah, this definition of this mobius function is little bit complicated, yeah. So also this mobius function is used in a lot of fields in number theory. So yeah, we can definitely use it here, and that basically solves the problem. So it's an interesting thing that, like, both zeta and inverse zeta have like n to the power s in denominator, so that's something cool. And yeah, so we have proved this thing, and we also saw how we can define the mobius function. So that is it for today's video, and I look forward to seeing you in the upcoming videos too.